So I'm going to talk about the quantum chemical calculation of NMR parameters for several thousand molecules, and I gave you this subtitle, a stress test for HQS tasks, and I'm going to get to that towards the end. Why am I stressing quantum chemical calculation of the parameters? Well, for those who are maybe not that familiar with it, there are two, in principle, different approaches to the estimation or calculation of NMR parameters. On the one hand, we have the quantum chemical side, and on the other hand, the empirical methods. And we in HQS pursue both of them for different reasons. So it's important to know their advantages and disadvantages. On the one hand, on the quantum chemical side, we have the accuracy that is in general much higher and can be also more or less controlled by the exact quantum chemical methodology that you use, and you get much more details about from the parameters by considering the electronic structure and molecular interactions at a really fundamental level. Another aspect is the transferability, so the methods can be applied to a really wide range of molecules without the need of any other empirical data or knowledge about them. So you can, in principle, use them for anything where you know that your quantum chemical methods also works, and you get a lot more insight into the electronic environment of the nuclei. You get more aspects about the three-dimensional structure, different conformations, and so on. So you get a lot more understanding of why the chemical shifts or couplings are the way they are. On the other hand, their computational cost is quite high, so these calculations can be very computationally intensive and time-consuming, in particular for larger or more complex systems. Also, the methods themselves are relatively complex, so you need to have a good understanding of the quantum chemistry that you want to use in order to know what you can do and what you can't. So this is also a barrier to get into it and to set up a whole workflow around it, which also took us quite a bit of time and is probably still not finished. And also due to all of that, to the aforementioned things, we have a limitation to in large systems. So the bigger you get, the longer the calculations take, and this does not scale linearly. This becomes very prohibitive for large systems. So this is also a limitation, and there's a point that might show some complexity is the equation that I have down here. So the chemical shielding sigma is calculated as a mixed partial second derivative of the energy with respect to the magnetic field and the nuclear magnetic moment. And this looks very simple perhaps, but depending on the quantum chemical method, or even for very simple things like Hartree-Fock or self-consistent field methods in general, this is already very difficult, and only a few quantum chemical program codes exist out there that have this implemented in an efficient manner. Empirical methods, on the other hand, are very fast. They require much less computational resources, so you can really calculate a lot of them in a much faster way. They are simpler to implement in general and also to apply, so you do not need to have that much specialized knowledge about it. So it's also applicable for almost everybody, and you make use of established correlations, so things that have been known for a long time, experimentally, for instance, some rules that were derived that can be applied there. However, in general, they are more restricted in their applicability, so you cannot just apply them to novel types of compounds or other unusual compounds where you do not have any existing data on yet. So you cannot do that, and also because of that or other things like the exact molecular structure or electronic structure is not there, so you don't have the accuracy that you get with quantum chemical calculations in general, and you might overfit them for a specific class of compounds, but then you do not have good data and you do not get good results for others. However, due to these advantages and disadvantages, at HQS we want to pursue both of them. So especially due to the speed and simplicity, and essentially every industrial researcher uses empirical methods for a quick prediction estimate of the NMR parameters, or the NMR spectrum for that matter. We want to have them, and we are developing them. So, but for that you need a good database. And where do you get that from? Well, in principle, you could consult literature and get all kinds of data that is out there. But the disadvantage of that approach is that you get data of different quality. So you don't know where it comes from. It might be theoretical, it might be experimental, and especially in experiment, but also in the theory, the conditions are different, so different solvent, different methodology, and so on. So it's very hard to estimate how good your prediction actually is. And for that reason, essentially, we decided to create our own database based on quantum chemically predicted NMR parameters. And this is where this comes in and why we've developed this workflow, which in a nutshell looks like this. So we start with an input, which can be a smile string or a two-dimensional structure like this one here, and then we need to convert it to a three-dimensional structure. So for quantum chemical calculations, you always need a three-dimensional structure. Then we need to do a conformer and rotamer sampling and do some post-processing. I will get into more details here later as well. Then we will do a structure refinement, and all successive steps are based on DFT in our workflow. And we do a screening of the structure, so everything that we deem is not relevant, we throw it away essentially. And only after all these steps and some screening, there are more details to it that are not shown here, we actually calculate the NMR parameters in the way shown here essentially, which is the most important, the most expensive step of the whole calculation. And after this calculation, we need to do an averaging over both rotamers and conformers, and then we convert the shieldings that we calculate to shifts, and from that we build a database which can then be used for the empirical prediction, where in general you just put in a two-dimensional structure and you get your NMR parameters out, put simply, essentially. All right, so one question that I had, or that we had at the beginning, where do we get several thousand molecules from, or how do we choose them? Well, in principle, you can come up with them yourselves, or you can ask ChatGPT whether that is a good idea or not. Is a different question, but we thought, okay, let's use something that is already out there for free, essentially, which is the PubChem database, which you can also search for by different properties that the molecules have. And since it is relevant for us, we looked at which molecules already have one-dimensional NMR spectra, in particular for 13 carbon and for proton NMR. And you can see here, there are many thousands or hundreds of thousands of molecules that we, of course, do not need. I mean, not all of them. So we need to filter them. And that I will explain in the next step. But what we took from the PubChem database from these molecules were their smile strings. And the smile string is something like this. It's essentially just a one-dimensional representation of a two-dimensional structure. And that we used as the input for the workflow mentioned here. Okay, but as I said, we need to filter them somehow. And how did we do that? Well, it's by different criteria. On the one hand, the smile string must be valid, so we must get a valid molecule from it. We must be able to convert it into a three-dimensional structure. Then we also restricted the atom types that are in there. So if we have really heavy metals, so to say, or other heavy atoms that we are not interested in, or that that the basis sets that we use are not defined for it, we excluded those. Then the next step was the number of atoms or heavy atoms. And with heavy atoms, I mean everything except for protons, which essentially is a measure of the size of the molecule. So the more atoms it has, the bigger it is. And also the more computationally expensive a quantum chemical calculation becomes, as I mentioned already before. And as I also said, this does not scale linearly. So if you double the size of a molecule, your calculation is not twice as expensive. It's in general, at least with the third power, so 8 times as expensive. So if one calculation takes 1 hour, if you double the size, it takes 8. But if you double it again, you're in a matter of days. But it can also be that one calculation already takes a day, then doubling the size takes 8 days, and doubling again, you're already in a matter of months. And this is, of course, prohibitively large. Then we took we restricted the number of rotatable bonds. What is a rotatable bond? For instance, if you look at the molecule up on the top here, this tryptamine, it has this linear chain here, and essentially you can rotate around those single bonds, and this is what a molecule does also if you have it in a liquid solution. And then you get different conformers. So you can see here in this three-dimensional plot all the conformers that we got out of a calculation, like in an overlay fashion. So these are different three-dimensional orientations of this chain here, and we need to consider them all, essentially, or at least all that are energetically low enough to be relevant. And for all of those, we need to perform individual quantum chemical calculations. So you know, the more conformers you have, the more calculations you need to do, the more expensive it becomes. And this is also, of course, then again a limiting factor when it comes to time, essentially. Furthermore, we restricted the number of methyl groups. So like those here, not necessarily because of the quantum chemical workflow, but another restriction. And these are the so-called rotamers. So if you look at the structure here, sorry, I don't know where there is this frame around. These methyl groups rotate, and then you can have 3 possible rotations here. And you can also have 3 possible rotations here and here and here. And all together, so I have 3 to the power of 4, which is 81. And then also you can rotate this hydroxyl group here. You get another factor of 2, so you have 162 rotamers. And in order to get a proper prediction of the NMR parameters, you need to know them all. And from our post-processing step, we try to find all of them. But if we have more and more methyl groups, then we have some kind of binomial explosion. And currently, our code cannot handle this. So this is what we still need to improve in the future. So we restricted it for now. Aromaticity is nothing that we really, that is a limiting factor, but it is a very important property. So many molecules are aromatic that especially pharmacy is interested in, or have aromatic groups. So we wanted to have a certain percentage of aromatic compounds in our sample. And this is why we also filtered for those in some sense. All right, just to make this clear again, the difference in our nomenclature between conformers and rotamers. So conformers are really different orientations. So in the 3-dimensional space, we have different angles essentially and dihedral angles between the molecules, which means they have different energies. Like in this plot down here, we have different conformers, different energies, and this means they also have different parameters, different properties. So we need to do individual quantum chemical calculations for all of them, but essentially, as I mentioned earlier, only for the relevant ones. And for this and the averaging in the end, these so-called Boltzmann-weights come in that are calculated in this manner. So if this number is close to 0, we throw them away. Rotamers, on the other hand, are non-distinguishable in principle. So only if we give these atoms numbers, which we do in some sense in our quantum chemical input, then they are different. But in practice, as I said, they will always rotate around it. So what you see is an average, and that's why you need to know all of them. You do not need to calculate all of them individually, since they are in principle equivalent, but we need to know all of them. And what we do is this kind of structure matching and then the ensemble completion. And in the end, from this matching and completion, we get permutations. So where this 1, 2, and 3 are permuted, and we can use those to average over the rotamer such that we get one chemical shielding for this methyl group here, for instance. All right, then how does the workflow go within HQS tasks, since this is what I did? So the whole workflow that I mentioned at the beginning is implemented in a piece of software of HQS, but then in a separate repository, we did implement an HQS task essentially, and did some other file logic and some other things around it. And then these wrappers can be called locally or so, like in a Python script or in a Jupyter notebook, but thanks to the HQS task infrastructure, the backend, so where the calculations are actually run, can be adjusted. So it can be on your laptop, but it can, for instance, also be on AWS, which is exactly what I used for all these calculations. So how did my workflow look after a lot of debugging and testing and so on? In the end, as I said, I picked those molecules and took the smile string and set up all the other settings for my calculations. And then I essentially started the calculation, but the code checks if the result already exists. So if I have it on my laptop, for instance, if yes, I'm already done because we have the parameters. If not, then the tasks are scheduled concurrently by the HQS task system. And this will then check if the results are already in the cache or in the cloud on AWS or so. If not, the calculation will be started. If yes, it will be checked if the task itself was successful. If not, well, we run the calculation again. But if yes, we can check if the calculation of the NMR parameters themselves was successful. If yes, we get them. And then if we start the same script, essentially, so the same input, the results will already exist and we will be done here. But if not, then the calculation failed, and this will be also noted. So then this will also abort here unless you really want to rerun the calculation. But it is important to distinguish between a failed task and a failed calculation. So the task, in the way we implemented it, will be successful even if the workflow failed, because but there are other issues that were present in the task system. Another aspect is that there are different cache modes. So I assume always to restart failed calculations, but you do not have to do that. You can also fully employ the cache, but then if the task was not successful, the calculation will not be run again, which is in general something we do not want. Or if you really want to rerun the calculation, even though the results are already there in the cache, you can use cache mode write only, and you will always run the calculation again. And yeah, I think that's essentially it. Like that, after many iterations, so going from tens of molecules to hundreds to thousands, I in the end calculated more than 10,000, and I had only like, I remember, something between 1 and 200 calculations that actually failed out of those that I started. So we have a database for the empirical prediction now that will be used in HQ Spectrum. And with that, I'm done with my presentation, and thank you for your attention.